Good afternoon, everybody. Welcome to this workshop. We have two, I think, interesting speakers here today. Of course, in line with the previous talk of Ross King. Oh, thank you. Our first speaker, I would like to introduce him. It's Professor Timothy Noel, professor at the University of Amsterdam, flow chemistry, but most of you know his work of the RoboChem. So Timothy, the floor is yours.
Yeah, thanks a lot for the kind introduction, and I was just using technology to make sure I'm not going over time. Yeah, thanks all for coming today to my talk and to this breakout session, and I would like to tell you a little bit the story about what we have been doing in the past 4 years on developing automated platforms. But before I do that, I would like to talk one slide about what actually drives us in our group. So we are really passionate about synthetic organic chemistry, but we want to use technology to really maximize the potential of that quite conservative fields. So what we are trying to do is to develop new synthetic transformations that exploit reagents or conditions that are very difficult to handle. But also we try to develop new tools that make synthetic life easier. And so, because this is not an easy field to convince, most of synthetic organic chemistry is still done in round bottom flasks. You see that everywhere. So the only way you can do and convince those people is by actually showing unique selectivities and reactivities. And the way we try to do that is by combining our skills in synthetic organic chemistry with chemical engineering principles. So if you want to know more, this is our website. Here you can find a full list of all the papers. Now, if you look at AI and how it has been changing the way we do things, then there are a couple of examples that we see in our daily life. Maybe you have been working with Siri, although I put it out. I don't like it too much, to be honest. Some people have used Alexa. I think we also see it, for example, in recommendation systems, which sometimes bothers you as well. But I think in some cases, like fraud detection, you could think, okay, this is a pretty good example. But I think where it really started to impact me a lot is, for example, ChatGPT, which helped me in maybe making my text a little bit better, more grammatically accurate. And so I think really ChatGPT shocked us in many, many ways. But also other types of systems that have been doing that. And if you look now like a little bit in the history of ChatGPT, in 2019, nobody cared about ChatGPT. It was not that great. And then all of a sudden it comes out, and here it had the brain of this bee. And then all of a sudden it has the amount of neurons that a squirrel has. And then it starts doing very cool stuff. And I think about 2 years ago, everybody was really impressed by the capacity that ChatGPT has. So the question is, of course, how is this technology going to fare? What is going to happen in a couple of years when we have maybe ChatGPT X that is going to be even more powerful? So the question is, how will these trends impact our jobs? Will there be loss of jobs? Will there be new ones? Or is this something that actually just freaks us out for a while, which ChatGPT definitely did in the beginning? But then we figure it out and we know how to work with it. And actually it's a great tool to help you in your daily life. I think for ChatGPT, for me, this is definitely, we figured it out and we learn how to live with it and we move on. So our group has been specialized also in photocatalysis. That's something that we really care about. And the way it works is you take, for example, a transition metal catalyst or an organic dye, and you shine light onto it, and it gets you into an excited state. And that excited state is now able to exchange electrons. So what you're doing is netto transferring light energy into redox type of reactions. And so why is this field getting so popular? Because if you just have a look at this Chemical Review special issue from a couple of years ago. So this was spearheaded by Paolo Melchiorri from University of Bologna. And you see that he was able to fill a whole issue with about 1,500 pages of new research. So this is really a hot topic that a lot of people care about in synthetic organic chemistry. Now, it's driven by technology because of LED technology. It provides you with a lot of mild reaction conditions. And what really targets or triggers the attention of the synthetic community is that it provides you with new opportunities. Now, just one slide about how we impact this field. So we were really trying to use flow technology to use undervalued molecules like methane and ethane, and to really get them at room temperature, activate them now with photocatalysis. And we are able to trap those radicals now and make useful molecules in a very efficient way. In the meanwhile, we have a couple of more papers on this, but it was really inspired by flow technology that allowed us to handle those volatile alkanes. So in this case, we just do two gases that we couple with each other and then target it with this one. The final example that I want to show you here is where we were interested in suffix chemistry. This is another volatile alkane, and this is a volatile molecule. It's a gaseous reagent, but it's also toxic. So this is a fumigant, actually, which if you have cockroaches or whatever in your room, this is the thing that they will inject in your room, and then they are all dead. So it's not the most benign type of gas to be walking around. So what we are doing is we take a liquid chemical that is abundantly available. We are going to direct that over a cartridge of KF. We convert that molecule into the gas, but that one never leaves the reactor, and you immediately let it react now with a nucleophile to generate those suffix reagents, which are interesting for click chemistry. Another very important topic within the synthetic organic chemistry community. Now, one of the things that we really do a lot in our group is how do we bring from a small, maybe 5 to 10% reaction, how do we optimize this to a reaction that is broadly applicable with a lot of high yields? So this is something that we thought in our group, it really takes us a lot of time to get to that. So it's both time demanding, but also it's quite cost intensive. And so how does this work? Let's say we are interested in this transformation. Based on that, we are going to randomly screen a whole bunch of reaction conditions. And then if we find a small hit, we are going to optimize that hit by varying one parameter at a time. Maybe we are going to change the base, we are going to change the catalyst, we are going to change the temperature, and we always take the best result one step further. Now, of course, this works pretty well if your landscape is not too complicated. But if you have, let's say, two parameters that work synergetically together, or two parameters that work antagonistically to each other, you will not be able to capture your global optimum with this type of procedure. Now, a couple of months ago, I asked actually this question to a synthetic organic chemistry community. There were about 500 people, and I asked, like, how many of you have actually used a DOE, design of experiments? And I think it was maybe 1%, 5 hands I saw. So everybody that says DOE is well established. Maybe in the industry it's like that, but it's definitely not in the synthetic community. Now, so with this approach, we might be able to still get this molecule in high selectivity and high yield. But the problem then, because of saving time, of course, what we are doing is we are going to take these reaction conditions and we are going to translate that to the entire reaction scope. But as like two humans are not the same. We all realized that when we were having COVID and that we had to have injections. For some people felt nothing after the injection with the vaccine. Other ones were feeling sick. So the dose was not adjusted to the body type that we have. This is the same that is the case for molecules. Like, these molecules have different electronic properties, different sterical properties. They are having different functional groups. So you cannot have the best type of reaction conditions. So you could do two things, right? You could either say to your students, I'm not happy with anything below 90% yields. But of course, yeah, I mean, a couple of those. I don't know how many of you would actually tolerate that. You would probably report me for harassment. So I tolerate that we have a couple of substrates that have suboptimal yields in our scope. And that is, I think, the strategy that most people in synthetic organic chemistry use. But of course, the question is, if you let a machine do that whole thing for you, then you have no excuse anymore. The machine can keep running all the time. So this is where we really wanted to go into photocatalysis. I already introduced the field a little bit, but one of the things that was really challenging for photocatalysis is that it's very poor to reproduce. And this has to do partially with the technical complexity. So if you have your reaction vessel and your light source, depending on how far you set it from each other, it really matters. And in the beginning, people were not able to reproduce it. But then when you asked it, oh, how is it possible that you cannot reproduce my chemistry? Yeah, then you figured out that they actually were using the wrong light source. So that type of stuff really happened a lot, and is really plaguing the field, that reproducibility, because of technical reasons, that it's not so easy to do that. The other part is that photocatalysis, there is behind or below the engine, the photophysics, the mechanistic understanding is not that trivial to elucidate. So if you don't understand the molecule that well, or the mechanisms well, you cannot always find the best reaction conditions. But of course, if you can let this do this optimization process without having to know too much about photocatalysis, that would be great. And that's where RoboChem comes into play. So we developed this robotic platform, which has actually 4 bays. The first one is our computer, where you have a Bayesian optimization algorithm. We also have a graphical user interface, and actually the RoboChem team is sitting there. They like actually the code more than the graphical user interface, as you can see here. But this is then actually the brain. So this is directing which samples need to be prepared. So here we have this robotic needle that makes up the reaction solution. Once we have the reaction solution, you inject that into the photochemical reactor. So this is a very powerful reactor that can be dimmed between 0 watt and the full maximum, which is more than 180 watt of optical power for blue light. And everything in between you can screen. And then it comes out of the reactor and is going to be analyzed by this inline NMR that reads out the yields and the selectivity. And that is then fed back to the algorithm that says, okay, then this is the next experiment you should run. So it's a closed loop optimization until you're satisfied. Now this was a lot of work to really assemble everything. We had to develop our own software. ChatGPT didn't exist, so we had to Python code everything by hand. Nowadays that would also go a little bit faster. And then we have here all the hardware. And then there are a couple of things. I mean, I'm not doing any justice here to really explain this. This is even dumped into the supporting information of the paper. But it's really a lot of small innovations that really made it really work well. I just want to highlight one of them. So for example, we are using these phase sensors. They are Arduino driven. And so every time this little reaction droplet is passing by, it's capped with 2 nitrogen bubbles. You will see here a change in this thing. So it functions as in essence as a GPS for your reaction segment. So you know exactly where it is in your system. So this allows us to do 2 things. First of all, you don't need to hard code what is the volume of your reactor inside there, because that one will just be, I mean, you know when it gets in, you know when it gets out, and that's your reaction time. The second thing is it allows you to park your reaction segment perfectly into the NMR. So that's where you can then read it out very well. So with very cheap type of technology, you can already have good control over all the system. Now this is the first reaction that we've been optimizing. So this is a very simple hydrogen atom transfer photocatalysis, where you pull off one of these hydrogen atoms, you generate a radical, and you let it react on this substrate. So this is a Michael acceptor, so Giese type of alkylation. You generate this intermediate, and so we give it a chemical space that we think that's where the best yield will be found, and then the Bayesian optimization will target, in this specific case, for maximum yield. And so what you're seeing here is that in the beginning you have an initialization phase, and so now the algorithm doesn't know any of the chemistry, and it's just going to do 6 of those, we call this latent hypercube sampling. It's going to check 6 type of things. It will see, okay, what is the readout on my yield now? And it will start learning what actually is the impact of those choices on the yields. And then after that phase, it starts to understand what's going on. And then it says, okay, great, I now know the system, and I'm now going to optimize for yield. It every once in a while comes back to these lower yielding segments because it also wants to not miss a global optimum. But you see after about 14 to 17 molecule iterations, you find the most optimal yield. Now the beauty with flow chemistry is that by feeding just more of the material, you can immediately scale those data points up to, this is about 1 gram, and you see that the 99% isolated yield, this is measured on the balance, is exactly the same as you see here, which is an NMR yield. Now this was the first result that rolled out of RoboChem, and Aiden, who is sitting there, he actually was texting me, and I just want to give you a snapshot out of that. So he was very happy, and then he was like, cocky as he can be, he said like, how about those yields? And you see, I'm very happy, right? And I used a word that I should not use in public, but anyway, I think it reveals how excited I was. Just to say that after that, I said to Aiden, actually, I said, give me a month, start playing with it, but give me a month to think about what we should do now. And so we came up with the plan to revisit that. Is really the scope in the literature actually as good as it should be? And so we took papers from the literature, and in the beginning we were always also a bit worried that people might think, okay, are you now trashing these people because you're finding better conditions? And that's actually not the case. Actually what we are doing is we are reproducing their work. We are showing that actually with an independent body, a robotic platform, this chemistry is reproducible. And you see that in most cases we are able to match the yields. In more difficult ones, like this one for example, these two are looking very similar. The only difference is that here this position is already taken by this carbonyl, so we'll start reacting here with hydrogen atom transfer photocatalysis. Now, so this means that this molecule could react first here and then there. So this is an A to B to C reaction, so a selectivity problem. Now what it finds is that by lowering the catalyst loading, by lowering the light intensity, you see that you can have a significant increase compared to the literature. And this means actually that the most difficult problems for like A to B to C reactions where selectivity is an issue, or maybe some sensitive molecules, those are the ones that really, that's where those robotic optimizations shine. What you also see is that every single molecule has now, let's say, a tailored reaction conditions to the sensitivity of the molecule. Because here, for example, this one can only react here, and now you can go all in with light intensity, all in with catalyst loading, and so it doesn't matter anymore. You now go for maximum throughput. So we also took some work from the Akita group in Japan. And so here there is actually one funny one. This is one you see here. So this is one reaction. This was the lowest on intensity that we had in the whole screening. Only 2 watt, and that was already sufficient. But you see there that you can have a significant increase. If you look at the literature of photocatalysis, there are not too many people that vary the light intensity. Maybe they do it once in the beginning, but never at the end. And so here you see how big of an impact this could be. For example, this molecule looks very similar, but here, because it's a quaternary center, it cannot react any further anymore, and now you can increase the light intensity again to almost the maximum that you can have. We also revisited a bit of our old work. So this is work that we did with Janssen Pharma. These are more drug-like molecules that are relevant in pharmaceutical sciences. And there you see the more complex those molecules become, the more benefit you have of refining the reaction conditions to have even, in some cases, like 30% increase. So we submitted the paper. We got 2 yeses and 1 maybe. This is trivial photoredox catalysis, that person said. I disagree, but the person wanted something like maybe dual photocatalytic cycles that are a little bit more complicated. So we actually did that, and so here we have, this is called metallophotoredox, where there is a nickel catalytic cycle working in concert with a photochemical cycle. And so you see here we have a lot of discrete and continuous variables that we are going to screen for. And then you see like the bigger the spaces, the more you can find actually better conditions than actually what we are just published 2 years before. So this is like doubling the yield of this specific one. Another interesting feature was that we found by manual 1 factor at a time screening that one benzophenone that was functionalized in some positions that we had to make ourselves was the best one, while we found actually that with a more rigorous screening that actually normal benzophenone, which is dirt cheap, is actually equally good in this specific case. Now the question is, of course, is chemistry ready for an AI revolution? And it's a little bit a mixed bag of feelings that you have here. Like, for example, this paper from Bartosz Grzybowski and Marty Burke, but also Glorious et al., they also found the same thing. So even if you mine a reaction like the Suzuki coupling, which is widely used, it's abundantly available in the patent literature, you still have trouble to find suitable reaction conditions for more difficult type of coupling reactions. And so they say, okay, this is caused by a couple of things. First of all, subjective preferences by the chemist. I've done my postdoc at MIT with Steve Buchwald. He has done a lot of ligand design. So I will be tempted to use Buchwald ligands. That's very normal. But if you were trained by one of his competitors, then maybe you would be more tempted to use those ligands, right? So, and these type of, like, depending on how our mentor taught us, that is also percolating into the literature. The other thing is the lack of reliable data and standardized data. So most of us don't publish too much negative data because, yeah, that's just giving the bullet to the referee and then they kill the paper right away. So that's also part of the academic problem, I would say. But on the other hand, also, like, what's the yield? Is it an HPLC yield? Is it a GC yield? Is it a yield isolated by a great student that did a good job? Or is it the yield by a clumsy student that dropped half of it on the ground and didn't tell me? Those yields are also in literature, and we don't know. So how do we fix that, right? So this is a fundamental flaw in current synthetic literature. So what RoboChem is giving us is actually labeled data. So this is what rolls out. So these are tables that roll out of, so these are 26 experiments. We do 5 factors that we are changing, and we get everything in between the best yield and the lowest yield. So here it shut out the light, and you can clearly see that light was a factor that had to be reckoned with. And the beauty is we are working now in flow reactors, so there is no mass heat transfer issues, no photon transport problems, no human error unless we make mistakes in the stock solutions. And we do have now the positive and the negative data available. So my belief is that self-driving labs will make a big impact in generating the data that will be needed to make this leap with AI, also in chemistry. With that, I would like to conclude that I think robotic platforms can become a game changer. We see that they are precise, fast, and information-rich, generating of data. I think what is also great, but I didn't actually tell you yet, is you just make your stock solutions, you press play, and then you can go somewhere safe where there is no reactive conditions. So it also helps you to do the chemistry in a much more safe way, so less risk of having actually accidents. It can capture multi-parameter space way better, and I do think that humans still have a role. So we still use the humans for designing where the chemical space is, to also debunk when there is a problem with the software and stuff. So I think it's going to be an ecosystem where humans and robots are going to work together. With that, I would like to thank the team. So actually the RoboChem team is here, they are there on that line. So Aiden, where is he on this picture? Actually, it's easier to point him there. And Pauline is our machine learning expert. I don't know if she's here, but anyway, she plays a critical role in that aspect. And I think, yeah, of course, we are already working with new stuff, so there is much more great stuff to see. And then we hope that we can share that with you in the coming years, maybe at a new session of ChemAI. Of course, the robots work for free, but they not. So I'm also grateful for the sponsors of the research. With thanks to them, I can pay actually the salaries of the human chemists. The robots work for free, so that's great. So let's see how many I can replace in the future. With that joke aside, I would be happy to take any questions. Thank you.
Yes. Yes, we have time for one question, and then we move on to the next speaker. And after that, we have hopefully a little bit more time for interaction. So, who has a question for Timothy right now? Yes, one.
Thanks so much. Hello. Thanks so much. To what extent do you think this technology can be scaled? What you showed us today.
What do you mean scale? Scale in...
So you have it in your lab, right?
How, like parallelization of robots, or...
Like so you have it in your lab, but how large can you go? Like to an industrial scale? Is it easy to scale or not?
Well, I mean, if you mean scaling in terms of making more material with this one, then we've done that. We've done that up to a few grams. But with a flow reactor, as long as you keep feeding starting material, you can keep tapping off product. If you mean scaling the robots, that you just have more in parallel, then I think we still need to make a transition to cheaper versions. Because one of the problems with self-driving labs is that you need quite a budget to be able to make those. You see already that if you look at the author list, we have one person for chemistry, we have one person for automation, we have one person for machine learning, and then a few that also help here and there. So it's not a cheap type of project to start with. But I think the democratization of self-driving labs, that's I think a big goal, and it's also something that we are interested in.
Okay,
and
thanks.
Then you can easily copy-paste it to other labs.
Well, thank you again, Timothy. So, yes, Martin, our next speaker has a lot of experience in automating and sparse data from Merck. Martin Fitzner is a lead data scientist and will share us how self-driving labs and Bayesian automation is working. Oh.
Try. Test. Brilliant.
Yes, are you ready?
Almost. The slides
Almost.
have to come up then.
Perfect. Okay, floor is yours. Yep.
To start us off, I would like to point out 3 words that are highlighted here on this title slide. The first word is Bayesian, because that's the method of choice for anything automation these days. Then there's industries, because I am from industry and I'll give you an industrial perspective today. And then we have BayBe, which for some reason I misspelled, but I'll explain that in a couple of slides. Disclaimer, so there is actually 2 companies called Merck, and I am from the German company called Merck. For interesting historical reasons, those are somehow related in the past, but today they are completely separate entities. You should know that, especially when you read press, which of the Mercks they talk about, especially if this is bad press, right? So you should not associate the wrong company with that. The second thing that's interesting about this company is, so first of all, it's super old. Merck is a super old company. You will find rarely any company of that size that is that old, but also we operate in 3 business sectors that are quite diverse. So healthcare, classical drug discovery, then there's electronics, which is semiconductor materials, and in between we have life science, which I would explain as sort of helper reagents, materials for both of the sectors above and below. For instance, if you've ever ordered from Sigma Aldrich, that's the Amazon of chemistry, that's part of Merck. And this makes my life quite interesting. It's also related to the talk because I work in a group function called digital chemistry, and I have the pleasure of working with these 3 sectors, which gives me a diverse set of problems to solve. So I have to think about methods which are applicable in several things, not just drug discovery, for instance. Yeah, in the 3 sectors you see here. So today I will look into the question, and I will propose, basically say that Bayesian industries should go Bayesian, so we should use Bayesian optimization. That's a very suitable method, and here is 3 simple points I made. So the first one is, some things just belong together, right? So you can see it here in the picture on the right. It's the same thing for a lot of industrial problems, and a certain kind of machine learning technology. And for most of our problems, it is actually Bayesian optimization. That is explained a bit by looking into some examples. So here are some rough examples that are quite diverse. So reaction condition optimization, we just heard about that now. There's other experimental design questions like cell culture media, biological assays. There's formulation problems, finding the right excipient for an already discovered drug. And then there's all kinds of processes. And on the very left, you see there's also a purely virtual kind of problem, namely hyperparameters for models. Yeah, that is also very good, very frequent problem we face in our machine learning teams. If, like, just seeing that, you would probably say, okay, these use cases don't have much in common. But actually, if you think about it a bit more abstractly, what we have is we have some parameters that we can change, like we have control over those, is the temperature, which solvent we use, and so on. And we have targets that we want to measure. So that's our goals. We have something that we can measure in a number, and we want to have it in a certain range or at a certain value. Now, in reality, it is very difficult to predict what should I set on the left to achieve something on the right. And this is why I call these problems black box problems. So most of the time, we do not know how to go from left to right. There's very few examples. For instance, when you, for instance, want to calculate the spectrum of a molecule, DFT is a very suitable method to do that. And you can do that and do not have to treat it in a black box way. There's an in silico model for that. But most of our problems do not fall into this category. We have no idea how this connection is from left to right. And we do not have the time to study that for several years. So that is definitely something, a problem in industry. We do not have the time to get mechanistic insights into everything. So the state of the art has sort of evolved to sort of tackle that problem by evolving around the black box and probing it. So it means we do not attempt mechanistic modeling, but we try some parameter settings. We measure the values, and then we observe our measurements. We try to learn from that and set some new settings. So I would classify it roughly in two methods. First of all, there's human intuition, experience. Of course, chemists know what they do. They have a lot of training. And for some things, that means they can run this optimization. At the same time, we heard about DOE and classical DOE. That is a method, apparently, that's not used in chemistry. I think one really clear problem with that is it is super bad with categorical values. So if you have high cardinality categorical parameters, DOE will not work. You have to do thousands of experiments. But in other parts, like mixtures or so, people frequently use these methods. You see, it's a very simple approximation. People, like DOE gives you a plan. It says you have to do this and that amount of experiments. Then we build you a model. Typically, it looks a bit like that. It's simple, linear, quadratic terms, and so on. Of course, that's limited. And so there's a new player on the block that is a little bit better at doing these things. And that's Bayesian optimization. So I do not want to go into detail so much about the details, how it works. But basically, the magic comes into play when you have a machine learning model, which is immediately better than this linear equation you saw. So a machine learning model is much better at capturing complex relationships, not limited to linear or quadratic terms. And the second piece of magic is you consider not just the prediction of the model, but you follow, or you take into consideration where the model is uncertain. That is highlighted here a little bit by the shade of the prediction curve. So if you combine these two things, the prediction and the uncertainty of the model, you can get a recommendation. You can ask the algorithm, where should I measure next? And the answer will be a mixture of, there I believe is the best point, and there I'm super uncertain. Because if you're uncertain, you should measure to build a better model, right? So these two things basically guarantee you to find global minima and global optima. There's another big point that is much different in Bayesian optimization. It is super flexible. So DOE gives you a plan. It says, do these 30 experiments, then you have your model, and we can look. Bayesian DOE, Bayesian optimization works from the first data point. You can build your model after the first data point, after the second, after the third. You can run things in batches like 5, 10, 15. And you can start also from several places that are really relevant. So you can start with no data, just doing a random start. You can actually use an old DOE and continue your optimization with Bayesian optimization. You could do a clustering to start off. And I will also, if we have the time at the end, show you how you can even use historical data, even on campaigns that are not identical to the one you want to run, if they are related. Very interesting, for instance, for chemistry. And another perspective why this method is a match made in heaven is just looking from the data amount perspective. So I brought this little ray here. Roughly, I would classify problems that I face as a data scientist on this ray, and often, let's look at the two ends first. So the left end is no data problems where it's so expensive to make a measurement, you can't do like 10 measurements or even one. You have to have the perfect zero shot. There, the workhorses are density functional theory or Navier-Stokes equation, CFD. This kind of stuff is really useful in that scenario, but most of our problems cannot be tackled with that. You cannot simulate everything in a computer. Complex layered materials, for instance, for semiconductor industry, lithography or something. Yeah, it's not feasible to study everything purely in silico in the computer. On the right side, we have the other ending, so all the fancy deep learning, reinforcement learning methods. They are only applicable if you have really large data sets. However, most of my colleagues approach me with sentences like this. We have some data, what can you do? Some data in this case means tens of measurements, maybe 100. Or they say, we have no data, but we're willing to do some iterations, some measurements. No colleague has yet approached me and said, Martin, I have 10,000 data points, give me some big data model. So that has never happened. This is very rare. And I don't know, maybe 80-90% of problems we face for materials optimization fall into this, what I call the low to no data regime. So we have either no data or are willing and have a few iterations of measurements. And that rings a bell now, hopefully, because that is amenable to Bayesian optimization very well. This is why, even some years ago, we decided at Merck to consolidate our forces. We had several codes in the company that did that. We consolidated that and open sourced it. So that is where this name BayBe comes from. That stands for Bayesian backend. It's fully open source and it has the least restrictive open source license. So it's Apache 2 and you can even use it if you like in commercial products. So feel free to check it out. BayBe comes with a lot of features that go beyond this purely mathematical core of Bayesian optimization. So BayBe is not a code for optimizing a mathematical or benchmark problem, but it's supposed to be used for real-world experimental things with features like, for instance, the chemical encoding I'll speak about in a second. Something I won't have the time to go into, but it could be interesting, is multi-armed bandits. So if you have A/B testing, want to do some campaign for social media or your advertisement departments, that's suitable there. You can do active learning, so smart data acquisition campaigns. There's quite a lot of features, and I've just, this is not primarily an advertisement talk, but all the results you're going to see is that is being done with BayBe, and feel free to check it out. Okay, second point. Bayesian optimization, if you try it out, is just better than the state of the art. We saw that also in the previous talk a bit. I have some more examples on that. Here is a very simple process optimization thing we got. We asked our healthcare colleagues, can you give us something we can benchmark? So those are people that work for decades with process optimization, for instance, for machinery doing tableting or something. Those are typically just simple numerical parameters, and they gave us a virtual process here, so we could properly benchmark it. Now, you see the results for the Bayesian optimizer in blue, and then they gave us their results with the DOE, which is the data point on the right. And you see already, the DOE has no trajectory. The DOE tells you, I need 29 experiments, then you have a model, and this is the point where you land after acquiring these points for the model. The Bayesian optimizer is much quicker at finding the same value, so you need roughly only 1/3 of the points of the experiments on the x-axis to reach the same kind of value. Also, it finds the best value earlier even than the DOE. So this is quite nice. It was a super simple example, so I said, let's try something more complex. We just added 5 irrelevant dummy variables. So now we're not optimizing 5 parameters, but we optimize 10. And 5 of them are irrelevant. Of course, in this benchmark, we act like we don't know which ones are irrelevant. That would be trivial, but actually, we have problems in a company where they have 80 to 100 parameters. Of course, many of them will be irrelevant, but they have no idea which ones. So this is what we test here, 10 parameters. The algorithm doesn't know which ones are irrelevant. How well can it work out? And you see the result is still good. I mean, it got a bit worse compared to the previous picture that is expected, but overall, Bayesian optimization still works. DOE is not on this slide, because DOE, the result for DOE would be over there on the wall. And to help, because I cannot print on the wall, we're going to zoom out now. So this is where DOE lands for 10 parameters. That's really not that much. So effectively, it means DOE cannot be used for this. So nobody would use DOE for this experiment, even if it's It's just 10 numerical simple parameters. I haven't even talked about categorical parameters, but this is where I want to go now. So categorical parameters are, of course, extremely relevant in chemistry, because if you change the solvent, the ligand, the base, those are categories, those are not just simple numbers. But machine learning cannot really deal with categories. So you need to turn your categories into numbers, and I've brought here a simple example. Let's look at these 3 molecules. So I'm not a chemist, I'm a physicist by training, but even I could see that the first and the third molecule are quite similar. And the first and the second and the third, they are not that similar. However, if you do this, what's called integer encoding, you just assign a number to your category, in this case the molecule, you can impose a spurious distance. For instance, now, number 1 and number 2 are closer together than number 1 and number 3. But I just told you, molecule 1 and molecule 3 are closer, are more similar. And molecule 1 and molecule 2 are not that similar. So you've imposed via this integer encoding something that's pretty bad, and this hurts the optimization because the algorithm basically has to figure this out or unlearn this or whatever. The other state of the art that's being used is one-hot encoding. You don't improve much. So in one-hot encoding, you have, instead of one number, you have vectors. The problem now, everything is equidistant. So all the categories are equally distanced from the other categories. And although there's no spurious order anymore, I just told you again, the first and the third molecule are more similar to each other than the first and the second. So there's a simple solution to that. Instead of this traditional machine learning encodings, you use chemical encodings. That just means instead of the approaches on the left, you provide reasonable chemical descriptors that describe your molecule. In this case, molecular weight, density, or boiling temperature. It could be other things, and indeed, there's many cheminformatics packages. So let's look at the result, the impact of this encoding. This is one of my favorite papers because it is a chemical reaction optimization. They have 5 parameters, 3 of them are categories, ligand, base, solvent, and they tried all combinations. This means for someone like me, I can go back and do a back testing. I can act like, please tell me how to optimize this reaction, and when it tells me, measure this, then I just look it up in the table. That's very valuable because we can benchmark our algorithms on that. So you see this is a very hard problem because on the right is the histogram for this reaction. Actually, most of the reaction conditions have 0 yield, and only very few have this really high yield at 100 or more. So here's the result you see with, this is run with BayBe and different encodings. So the encodings here you see in blue and in orange are exactly those cheminformatics encodings. You have then the one-hot in green, a random baseline, and I also put up Optuna. Optuna, maybe some of you heard of that. That's kind of a gold standard in data science for Bayesian optimization, especially often used in hyperparameters for models. So what we see here is 2 things. Chemical encoding makes a drastic difference. So I have these dashed lines. They are guides to the eye to see, let's say I want to stop after 90 yield with chemical encoding. So blue curve, I need to do less than half of the experiments than with the one-hot encoding. I think that's the other line. So drastic improving just because I display my molecules in a different way in front of the algorithm. So very powerful and comes almost for free. And the second one, Optuna is not fit for the task because there's, okay, let's not get into the topic, but let's just say Optuna is a mathematical optimizer. It's not made for these real-world experimental campaigns. You can see that here, and we can talk about why. I'm happy to say that because this works so well, we have now, with the next release, we will be putting out not just the ones you saw as encodings, but 34 different kind of chemistry encodings. So if you ask your cheminformatics colleague, they might be able to select the right one of those. If you have no idea about cheminformatics, this is all just cryptographic names, but there's really specialized descriptors for different types of molecules. And if you select the right one, your optimization might be better. And here, let's jump a bit, also in the interest of time, to another example. Because, like I said, Bayesian optimization is just better. You see here another example, completely different. It's not chemistry, it is a container design. So Merck has some specialty gases that we sell and ship, and they need to come in specialized containers, and in this case, they need to have a good outlet saturation. So what people do is do cut designs of these containers and then do very, very expensive simulations. So I think this takes a week or so per simulation, so you can't do millions of simulations and just pick the best one. Instead, they let loose the Bayesian optimizer onto this problem and asked it, gave some rules how to design and change the container, and then observe and measure the results. So you see the human trials, you see them on the left, and on the right you see the ones that have been obtained with Bayesian optimization, and the highlighted result is better than everything they did before, not by a great margin, but it is better. So immediately the algorithm found something better. But what I find remarkable here is we got the feedback that actually this was a surprising design. So the engineers were like, we didn't think of that. And now, I was told they even went back to this simulation, studied it in detail, and trying now to learn new design principles. So that was a fantastic outcome. I was really happy about that, because not just it's better in terms of the metric, but also in terms of convincing people to use it, because they can be inspired. We can break out of human existing biases. Okay, last and third part, going beyond just better, looking into new use cases. So because earlier I think I showed you this process with 10 parameters. You couldn't even do that with DOE. With Bayesian optimization, you can do it, and there are other new things that you can do with Bayesian optimization. So one thing is self-driving labs. The hype is here, definitely, but it's actually very hard to get a DALL-E or so to generate your picture of a self-driving lab that has no wheels. So that's what the algorithm thinks. I will show you in a second what we think this lab looks like, but this is an important topic also in industry. Automation has several layers, so automating your settings, like automatically running recipes, is very big, but we want to automate the entire loop, so the measurement, the recommendation, and the setting of the new settings, measure that. And this is why we did a prototype, also in a flow chemistry laboratory. This is our prototype, prototypical reaction. Very simple. I mean, not like super trivial, but this was a simple reaction we tried as a first guess. It has a side product, and this is why I picked it, because it's not just one quantity we're optimizing, not just the yield of the main product, but we also want to minimize the yield of the byproduct, so multi-target problem, and it had 4 parameters that you could change. And here's the result, running through its time completely autonomously in 6 hours or so. And the result, I think the most important one is on the bottom, where you see the blue curve shoot up and the orange curve remain down. That's exactly this yield that I want to keep up and the second yield I want to keep down. So this worked pretty well out of the box. The biggest challenge here is software and integration. So going into the labs, and Merck has many, many labs, people have many, many different equipments. The main work is not anymore the algorithmic thing. I think this is close to being solved, can always be improved, but this method clearly works. The problem is, when I come to a lab, I need to write interfaces to the equipment to enable this full automated loop. So that's the problem. And lastly, I still wanted to bring you back into reality. So not every flow chem lab looks like the one you saw generated by DALL-E. This is the real world. This is this was the flow chem lab you saw this result from. And it's very, very important to also, not just think in terms of automation and robotics as these new kind of labs that are fully newly built. We also want to bring automation to existing labs because we have many of them. So we can't just throw away all of that equipment. We want to automate those as well. So I think, one more word about that. You know what I just told you is also a mindset thing. Whoops. I guess I don't need that. Can you still hear me? Yeah. It's also a mindset thing, and to help with that, we wanted to upskill our colleagues. So you actually see here a picture from a little workshop that we held, where we received these little self-contained self-driving labs on a Raspberry Pi. This is in collaboration with the Acceleration Consortium, and those have a sensor and an LED. And then we had this workshop where they had to build this little Raspberry Pi, and they were going through it with different algorithms. So it was an exchange, it was building something physically, and it was also looking at the results of different algorithms. So we also did something like that, and I think this upskilling to keep colleagues on board who are more practically minded is very important. I don't know what the time says. If I have time, I will speak about one more topic. If not, then I will skip this. Okay, then just let me show the thank you slide. This, I just said the algorithm works, but I didn't mean to say there's no improvement, right? So there's many things still on our roadmap that we are working on. If you're interested in any of these for your automation, your optimization, feel free to reach out. In the future, we will have these in our code. Lastly, if you have any questions about the code, the method or so, feel free to reach out to me at SciFits. And with that, just thank you for having me.
Yes. Thank you, Martin. So I'm almost thinking, is there anything negative on Bayesian optimization?
Yes, actually, yeah.
Okay.
You can be. I think one thing that I'm thinking about that is not easily done with Bayesian optimization. You know, I'm theoretically minded, so it's maybe not a very practical answer, but it's nested spaces. So nested spaces where you cannot do a simple tabular description of your problem and your design space. Bayesian optimization is a bit harder for that. For instance, molecular generation and molecular design. You know, typically people think of that as a backbone of a molecule. Then you have R groups. For that, you could use Bayesian optimization, but no chemist wants to keep in those bounds when they design their drug molecule. They want to have more flexible changes. So this is not easily represented in the design space in Bayesian optimization. So for that, I think there are better methods like reinforcement learning, for instance.
Yes, okay. Well, now it's time for both of our speakers. Who has some questions? No hands? Yes, of course. Yeah.
Okay, it's about what you do in the Bayesian optimization if you have different experiments cost different, you know, you've got a choice of experiments and they cost differently, so often large amounts of difference. Can you deal with that?
Yes, okay.
Yeah,
so there's something called multifidelity, and this is just sort of a more discrete way of what you just asked. So if we think about the cost of an experiment as a continuum, but we also can think of it in categories. So for instance, instead of doing the measurement, I can do a simulation, and there's multifidelity methods to sort of run on the low fidelity experiment and have cheap cost for acquiring experiments, and only do an expensive one when it's needed in terms of the model. So that goes a bit the direction you asked. So taking cost into consideration is possible.
Is it built in your system now?
No, currently not. So multifidelity was on the roadmap. That is mostly because multifidelity is easily treated when you have multi-output models. Currently, we still are on a scalarized model. So we have only one output. But it will be, it's actually the next big upgrade we are working on is this Pareto optimization. And that will have multi-output, and with multi-output will come multifidelity. So I would say soon.
Any other questions? Oh, yes, the hand coming up. Yes.
I'm curious about the possibility of using this methodology in using it to make new productions, because as far as I can see, it's to be used for the stability of the production itself when it is already going from behind. But what if you want to use it in a new production? How to deal with this?
So I'm not quite clear what you mean with new production. Like what characterizes new production for you?
Well, in our industry, we are having too many products. For example, if we want to produce a new product, what would be the way to reach within this methodology? Because you are always using the historical data to understand the behavior of the product and find the ways to make it better. But what about the new products?
You can just do a normal campaign, have the target of your new product measured, come up with design space. That is the challenge then, right? You have to be smart about the design space. You can maybe start with a larger one in the beginning, but in that sense, a new product doesn't differ from optimizing a reaction or something else. So I don't think I don't see at least how it would not work for a new product. Yeah, and we have that. We have material science problems which become new products. They are run in that manner.
Okay, thank you.
Yes. Any other questions? Yes. Oh no.
What is your view on the training of future chemists at universities, considering these new technologies, compared to the past and the traditional way of chemistry learning?
Yes.
Well, it is the same as with flow chemistry. You just need to put it into curriculum. And I always say a student doesn't care which recipe they need to execute. They will learn it. So they need to learn new programming. They need to learn a little bit of engineering. I think the future chemist is a multidisciplinary one, not like the old way. But it's still very important to understand chemistry very well, because if you, as we shown also in our system, we need to design the space very well, and that's where the chemist comes still into play. So you can let the, let's say, the time-consuming task of optimizing that you can let do by the robot, but you still need to come up with a good idea, and there is still a lot of bottlenecks that you need to solve. So I think investing more in multidisciplinary courses where everything gets done. But we see also in our group that actually if you train on this, you can learn this actually. I don't say you will always understand the principal chemical engineering things, but if you have gut feeling engineering, it could be already enough. Most of the things, I always use the analogy to MacGyver, right? If those of you that are old enough remember this guy. In the 80s there was MacGyver, and he always got out of trouble by just duct taping everything together. That's sometimes a little bit how we do stuff as well. You have a problem, you fix it. And that's how you need to do it. Of course, without a doubt. Because I think it doesn't come out of the blue. Like for example, new reaction discovery. There are some people that work on this, like completely new reactions. The ones that are published are sometimes not that exciting, or not, well, they are already known, but you didn't find it. So a good knowledge to steer where we are going to find new reactivity, that is definitely needed, 100%.
Yes, merci. Final question. Who has a final question? Oh, there's one. Oh, I'll move this side. Hang on. Yeah.
Applied everywhere.
Yes, you are.
Thank you. Yeah. So, really like the note on MacGyver. MacGyver was the person why I studied physics, so great. So, if you would combine these two technologies, what would happen? BayBe and RoboChem?
Actually, that's already done, right? Because we use Bayes in optimization. And actually, to answer your question, we do multi-objective. We simultaneously optimize for throughput and for yield. But there is nobody that says you cannot factor in the cost price. So if you want to minimize the cost price, you could do that as well. And then you get a Pareto front with all the most optimal solutions.
Having said, that was the closure of this session. Well, big applause for our speakers. We have a 5-minute coffee break. Yeah, 6 minutes. 15. Oh, 50 minutes. Okay.
I don't know what is this even.
It's fine. We can put it
Just
back
goes in
yes.
that first.
Thank you very much.